Our final speaker is Professor Norbert Schuch, who is the group leader of the Entanglement of Complex Quantum Systems group at the Max Planck Institute for Quantum Optics. He is an expert in tensor networks, which he uses to investigate the classification of entangled quantum matter and the study of strongly correlated systems. And in his talk today, he will discuss an entanglement-based view of quantum many-body systems. All right, Norbert, the stage is yours.
Thank you very much, Amanda. Thanks a lot. Can everyone hear me? Yes, good. It's great to be here, even if only online. I noticed I got completely out of exercise in giving talks due to the current situation. So in my talk, I would like to explain, to tell you how a perspective from quantum information, a perspective from the point of view of entanglement, can give us new insights on quantum many-body systems, can lead us to understand better how quantum many-body systems behave and get new insights. So complex quantum systems, quantum many-body systems, is something which appears equally in quantum information and computation and in quantum many-body physics. So for instance, in condensed matter physics, in complex molecules, or in high energy physics, for instance, in quantum chromodynamics, we are facing complex quantum many-body systems which exhibit intricate entanglement. But also if we run a quantum computation, what we have is basically a complex entangled quantum many-body state. Or if we carry out, for instance, a measurement-based quantum computation, what we're doing is we're using complex quantum many-body states to carry out computation. So there's a close connection in both directions, right? So we can use ideas from entanglement theory to understand the complex entanglement patterns of these complex quantum many-body phases. But we can also conversely use complex quantum many-body systems to store quantum information, to process quantum information, for instance, in topological quantum memories. And this basically, this gives rise to basically a field at the interface of the two areas with two types of questions. First, to study quantum many-body systems from a quantum information perspective, but also conversely to utilize quantum many-body systems as a tool in quantum information processing. And in my talk, I would like to highlight some ways in which the first aspect helps us to get new insights. So what do we mean by complex quantum many-body systems? Well, we mean systems which are composed of many quantum particles. And as I said, they can appear in the study of complex solids, of complex molecules, but also as the output of a complex quantum computation. And since we have many particles, the point is that we are faced with an exponentially large Hilbert space, but it also has a special tensor product structure. But still, it's this huge space, so we have no way of describing it in a succinct way. So how can we deal with that space? And a key insight is that both in quantum computation and in quantum many-body physics, we're usually concerned with very special states. So we are looking at states, for instance, which are low energy states, thermal states, states obtained by the time evolution under some local interactions because the laws of nature are local, or we're looking at the output of a specific quantum circuit. So what we end up with is that all these states lie in a very tiny corner of our exponentially big Hilbert space. And we really want to know what makes this corner special. And this leads to the question, what is the entanglement structure of these interesting complex quantum many-body states? What is the entanglement structure of these complex quantum many-body states? And if we're interested in states at low energy, at low temperature, in ground states, in low-lying excited states, it turns out that, well, the locality of the interaction will also govern the locality of the entanglement, because the entanglement tries to satisfy, to minimize the energy, and the energy is given by a local Hamiltonian. So it turns out that this means that the entanglement will be distributed locally close by, between close by spins, but not between distant spins. And this can be formalized in the so-called area law of entanglement, which says if we take any region like this region here, then the entanglement between this region and the outside will be proportional to the boundary of that region rather than the volume of that region. Okay, sorry. So it turns out that what makes this region special is exactly this entanglement property, that the entanglement is basically proportional to the boundary. And if you know quantum information, you know this is a very special property, because for a generic state, the entanglement will be proportional to the volume. So these states are very, very atypical. They have some very special properties. So how can we use this special structure, this locality of the entanglement, that it only sits next to the boundary, to build up an ansatz to describe these states? So the idea is that we take each of the particles and consider it being built from two auxiliary particles, and these auxiliary particles are placed in maximally entangled states. So now we have these particles which are placed in maximally entangled states, so-called bonds, and these bonds build up indeed entanglement in a local fashion. But we also see that if we cut any region in our system, the entanglement between that region and the outside will be, is this box shown where it should be? No, something is, sorry. Amanda, did the annotation work the way it should? No.
I saw a box, but it was around your state. I'm not sure if that was what you intended.
No, it should have been around the bonds. So
the bond,
not working.
Yeah.
No, indeed, I also saw it there, but I thought maybe it's only my screen. Okay, then I'll just use a mouse to make annotations. So no formulas, but I didn't plan to anyway. Okay. Sorry. Right. So it means that whenever we cut any region, indeed the entanglement will only be across the boundary. So this ansatz captures the right structure using these entanglement degrees of freedom here. But of course, we need to do a bit more. So we will apply some linear map, and putting this linear map will allow us to take these auxiliary degrees of freedom and build some interesting state out of it. And we can also formulate this in a more mathematical way, where maybe the role of entanglement is a bit more hidden, but it's maybe more accessible mathematically, where we think of this map as a 3-index tensor, mapping 2 entanglement degrees of freedom to 1 physical degree of freedom. And this maximally entangled state basically is like a delta function which identifies and sums the indices. So we get a contraction of these tensors. And this finally allows us to express this complex quantum many-body coefficient, this exponentially big object, as a contraction of simpler tensors. And that's why these states are termed tensor network states, or in 1 dimension, because this is a product of matrices, matrix product states. We can do the same in 2 dimensions, again, by starting from entangled states. Again, the entanglement will only cross the boundary of any region. Or we can alternatively think again of this map, which maps the entanglement to the physical system as a 5-index tensor and arrange it in a grid and contract. Now, this construction, of course, is not restricted to square lattices. We can do it for fermions in higher dimensions. We can do it in the continuum, in fact. And I have motivated this construction from the point of view of entanglement. I've said it basically captures the right entanglement structure, but this was really an intuitive argument. So can we make this rigorous? Is this actually a rigorous argument or just an intuitive argument? And it turns out, for instance, in the case of matrix product states in 1 dimension, it can be proven that for pure states in 1 dimension, this is indeed the right structure. And the way the argument works is that for any cut I do here, if the entanglement is small, I can find an efficient approximation with a small rank across this cut, a so-called small bond dimension. And then I can just glue these cuts together. And it turns out if I glue them sequentially, basically by projecting onto this lower dimensional space, I get a nice and controlled error. I get an efficient approximation. Now, of course, in reality, we're interested not only in pure states, but in mixed states. States in the experiment are mixed. If we describe dissipative systems, we have mixed states. And we could try to describe mixed states in the same formalism, but will that work? Will a low amount of entanglement also guarantee us an efficient approximation? And it turns out this is actually not a trivial question, but we're able to resolve it recently. And it turns out that first of all, one has to look at the right entanglement measure. We look at the entanglement of purification, because if this so-called entanglement of purification, which is a well-known entanglement measure, is low across every cut, then we can find an efficient approximation in trace norm. And this trace norm is important because it means that all observables are indeed faithfully approximated. It's a distance measure we actually care about. So we have all these good approximations in trace norm. And now you would think we do the same as before, but it turns out we're in trouble here because we want to use a trace norm, and the trace norm doesn't define a Hilbert space, it defines a Banach space, and Banach space projections are far less nice than Hilbert space projections. They can blow up your vectors. So it turns out if we do the same as for the pure state case, our error will blow up exponentially and we will not get an efficient approximation at all. So it turns out what we have to resort to instead is some renormalization type, some tree type concatenation. And if we do that, it turns out we actually do get an efficient approximation. So using a suitable type of area law and a suitable type of concatenation, we can actually find an efficient approximation of also mixed states relevant to describe realistic systems by such tensor networks. Okay, Now, we don't necessarily have to resort to the area law. One can also directly prove that one can approximate ground states and thermal states efficiently. Again, in trace norm, which is important. And again, efficient means that things scale nicely. They scale polynomially in the desired precision, but also in the size of our system. And again, the proof is quantum information inspired, because we can do, for instance, a Trotter decomposition of e to the minus beta h, and then realize that each step in the Trotter decomposition, which brings us closer to the ground or thermal state, only introduces very little entanglement. So we can use a compression scheme to compress the amount of entanglement we need to a much smaller amount. And one nice feature of such arguments is that we don't need to take a detour via the area law, which turns out in 2 dimensions is not sufficient, because it doesn't tell us how the entanglement is distributed, and we would need that for a proof in 2 dimensions. Now, one more thing is that these states, these ansatz states, do not only approximate ground and thermal states and states with low entanglement efficiently, they also form an exact representation of a wide range of relevant states. And we will meet these states later on, but in case you know these states, so non-chiral and also chiral topological models can be exactly represented. The so-called resonating valence bond state, we will meet all of these later in the talk, can be exactly expressed. So states with strong correlations can be succinctly expressed with very few parameters. And not only do these states provide an efficient approximation for ground states, they also conversely appear as exact ground states. So we can construct exact Hamiltonians if we impose specific conditions. And these Hamiltonians will have these states, these MPS or PEPs, tensor network states. Did I mention the 2-dimensional version is usually called PEPs? So whenever I say PEPs, I mean 2-dimensional tensor networks. I think I forgot to stress that on the last slide. So these Hamiltonians will have these states as exact ground states, and the proof idea is basically based on saying that these Hamiltonians make sure that locally the state looks correct, and then we want some kind of consistency check. We want to be sure that if things look locally correct, they look globally correct. If we can prove that, we have proven these conditions which give us a unique or a controlled ground space. All right. So the first message is that the language of tensor networks, of matrix product states and PEPs forms the right language to describe quantum many-body systems by understanding what structure their entanglement has and then encoding this entanglement in a wave function for a system. So a second important aspect is that tensor networks allow us to encode the structure of a model of a Hamiltonian, the structure of the physics, which means symmetries, the way the Hamiltonian transforms under lattice symmetries, under spin rotation symmetries, and so forth in a local fashion. So for instance, if we choose this encoding here, we choose a tensor where if we act with a unitary transformation on the physical system, for instance, this will correspond to a different unitary action on the entanglement degrees of freedom. And now you can see that if you make a network out of these, you will always get one V and one V dagger together. They will cancel because they're unitary. And we will actually get a symmetric global wave function. So we can locally encode all the symmetries, which is a very powerful thing. We can take global properties and make sure that we get them from a local constraint. And these symmetries are nicely also reflected in the corresponding Hamiltonian. So we really get models which describe symmetric states in a nice way. Now, a key question for us is, what about the converse? So can we conversely say, if we want to encode a specific symmetry, can this always be done, for instance, in this way on the left? Or are there more general ways to encode the symmetry? And this is a very important question, because choosing the most general way to encode the symmetry allows us to describe the most general phases a system can take. And this is why these converse statements is something we term fundamental theorems of matrix product states and PEPs. And they can be proven for a range of systems. They can be proven for all one-dimensional systems once they're brought in a suitable canonical form, which is no restriction. We can also prove them for 2D systems on any kind of lattice with unique ground states. And more recently, we have figured out how to prove them for a general class of models which has a structure to exhibit topological order. But it also turns out that our big hope that we can prove the most general such statement is in fact impossible, because it's actually undecidable to figure out if 2 such states are related by a symmetry. And this can be proven via a mapping to tiling problems, which are also known to be undecidable. But the good thing is that this only tells us this will happen if we don't impose extra conditions. So it really tells us that we should better impose some extra conditions. which makes sure that this doesn't happen. And then it tells us that tensor networks, oops, that was the wrong direction. Then it tells us that indeed the language of PEPs provides the right framework to model and to study quantum systems and their symmetries, the way the symmetries interplay and give rise to different phases from a local perspective. So by encoding all the physics here in some tensor and getting both Hamiltonians and ground state wave functions basically on an equal footing. All right. So what can we do with this language? Well, I already mentioned topological order, and topological order is some very interesting and exotic order, which is kind of hard to describe, but it turns out that PEPs form exactly the right language to describe this type of order. So in order to explain you what topological order is, let me first explain you what it is not. So what is conventional order? Landau theory. Something we understand very well. Well, so what we have is, for instance, a classical magnet. Magnets would like to align in parallel, but as we heat them up, here on the left, the system becomes hot and disordered. But if it's cold, the magnets align in parallel, or we take a one-dimensional quantum Ising model. So if the spins would like to align in parallel in the z direction, up or down. But if we impose a strong magnetic field, they will align along the field in the x direction. And all of this can be identified by checking local properties, local order parameters. That was Landau's big insight. So we can check basically if the spins choose a preferred direction relative to the rotational symmetry. So we can, for instance, in the Ising model, measure the Z magnetization. And this means just looking at a single spin and averaging overall spin. It's a local property, and this will tell us in which of these two phases we are. So it can identify phases. It also allows us to label and count the different ground states. So we know that the Ising model can align in two directions. There are two ground states, and the value of the order parameter will tell us which phase we have. And if we add a small magnetic field in the z direction, we'll pick one of the ground states. So it gives us full control over the ground space structure. And now what is topological order? Well, topologically ordered systems are systems which don't behave this way. So systems which are not disordered because they have several ground states. So for instance, we put this system on a torus, it will have, say, 4 ground states. Then again, we put it on a sphere, we will have 1 ground state. And this dependence on global properties already tells us that there cannot be local order parameters because they would allow us to count how many ground states there are based on local properties. But suddenly this depends on global properties. This also means that these states are in fact very well suited to store quantum information, because if there's no local way to distinguish these degenerate states, there's also no way for noise from the outside to destroy them, because any noise which would destroy them would also be able to distinguish them and would form an order parameter. These systems are also very interesting because they have exotic excitations, excitations which have non-trivial statistics. Spin systems for excitations have fermionic statistics, or even more general phases, or even matrix actions, non-abelian phases, which can be used to encode quantum computations. And they also have other interesting properties, like, for instance, exotic protected edge physics, like in the fractional quantum Hall effect. And all of this means, because there is this degeneracy, there must be some order in the system, but it cannot be local because there's no local order parameter. So it must be some global order in the quantum correlations in the system in the entanglement. And as I said, this is why it can be used, for instance, to store quantum information or carry out quantum computations by moving these excitations around each other. So as I explained to you earlier, if we look at conventional order, which relates to conventional physical local symmetries, these symmetries can be encoded locally in the tensor by saying the physical symmetry action should translate to a symmetry action on the entanglement. But do we have a chance to also understand what is going on in topological order? Can we also understand this from a property of this tensor? And one might think no, because it's a global ordering of in the entanglement, but we have access to the entanglement here in a direct way, which we usually don't have. And it indeed turns out that topological order is rooted in some local symmetry, but it's a pure entanglement symmetry, right? There is no physical symmetry action whatsoever. And the reason why such a pure entanglement symmetry is very powerful is something we see if we take this equation on the left and we take these 2 U daggers and move them over to the other side. So we get this equation here on the right. And this equation basically tells us that we can form strings of these UGs. And if we have such a string, the string can be moved, right? This equation tells us that a string from the top can be moved to the bottom. So we can move these strings around freely in our system, which in particular means that these strings are a global property. They cannot be seen locally, because if any Hamiltonian checks if there's a string locally, well, I could move it somewhere else, so it's not there. Now, it turns out that if we suitably generalize this not only to simple group actions, but to correlated actions, for instance, using Hopf algebras or matrix product operators, so tensor networks again, we can indeed describe all topological phases we know of. Now, what does this symmetry really tell us about topological order? Well, one thing we can do is we can take these strings and put our system on a torus and wrap such strings of group actions. So for instance, in the case of a Z2 action, we would have a Pauli Z. So we could wrap a Pauli Z or no Pauli Z in either direction. It turns out this parameterizes 4 different states, but these states are indistinguishable locally because we can move these strings anywhere we want. So we get a degenerate ground space. We can understand from this local symmetry how we will get a degenerate ground state, and we can explicitly parameterize it, which gives us direct access to probe it. And we can also directly describe these exotic excitations, for instance, by putting such a string in our system, but letting it end at 2 points. So the string again can be moved, but the endpoints are there. So they form excitations which naturally come in pairs, which is a defining property of anionic excitations. And we could also put a dual excitation. So for a Pauli Z, we could put a Pauli X somewhere. And then if we move these things around each other, you will see there's an anti-commutation. So you naturally expect a -1 phase if you move these guys around each other. So we can explicitly understand where these exotic statistics and these exotic excitations come from and their statistics comes from. And we can explicitly construct them, which gives us access to these excitations in a way which we can use, for instance, numerically to assess their properties. So this is very useful analytically to study the different phases in these systems, but also numerically to study systems away from fixed points, cases where we don't know in a usual language how to describe these excitations, where these excitations get spread out over a length scale on the order of the correlation length. Whereas in this entanglement language, they're kind of a twist in the entanglement. They stay strictly localized and we can build them exactly. So message here is that PEPs, tensor networks, allow us to encode global topological order which is a global property of the entanglement through local symmetries of the entanglement because we have direct access to these entanglement degrees of freedom. So what can we use this for? So one thing I would like to illustrate is how we can use this to define order parameters which allow us to microscopically study topological order. And what I mean by that is really that, well, if we think of conventional order parameters, they are not only good to distinguish 2 phases, but if you look at the magnetization in the Ising model, you will see it goes to 0 with some specific curve, with some specific critical exponent. And these exponents are really a fingerprint of phase transitions. They characterize what is known as a universal property of phase transitions, which relates to the fact that phase transitions usually fall into a number of separate universality classes, which don't depend on microscopic details, but really only on the long wavelength physics. And where very different systems can actually have the same universal behavior. So how do order parameters work? Let's look again a bit closer at conventional order parameters and then take some inspiration from there for topological order parameters. So let's look at this 1D Ising model where the spins would like to align in parallel in the Z direction, but if you put a strong field, they will align in the X direction. What's the symmetry? Well, the symmetry is a spin flip, right? So it's a Pauli X tensor N. We flip all the spins. So the corresponding order parameter would be the Z magnetization. We know that, but we also see it from symmetry reasons because it anti-commutes with the X. So it measures symmetry breaking. And one way to think about this is that in the disordered phase, in fact, right, the one which has a 0 order parameter, it creates a local excitation. It will take a spin and flip it in the opposite direction, the Z, because it's oriented in the X direction. And this kind of twists this state. It creates a local excitation, an excitation in this state. And so the state becomes orthogonal to the original one, and that's why this expectation value is 0. Whereas in the magnetized phase, it will give a plus or minus sign depending on the phase, so we can distinguish the phases. But the point is, it's not only interesting on this side, it's very interesting what it does here, namely it twists our ground state in that case, and that's why it gives 0. It turns out we can also define some dual order parameters. Some people call it a disorder parameter, where we basically take the half chain and say, let's just flip, let's apply the symmetry, but not to the full chain, to half the chain. So if we do that, you can see this on the right here. Where's my mouse? You can see this here on the right. We will create domain walls, right? We will flip half the spins. We will get a domain wall. So again, we twisted the ground state. And this means that this thing will again have 0 order parameter because now we're orthogonal to the original state. Whereas in the magnetized state, which is anyway an X eigenstate, this doesn't do anything. So we get a non-zero expectation value. So order parameters come from the symmetry, but they also act by creating local excitations, by creating twists actually in the state of the system. And this is what is important. So let's take this as a way to think how could we create order parameters also in topological phases. And our starting point is this entanglement symmetry, which we talked about earlier, which is characteristic of topological order. And I illustrated here for a Z2 symmetry. So we have a Pauli Z symmetry, for instance. Now, it turns out that if you concatenate all these tensors and we leave a boundary somewhere, these symmetries will all cancel in the bulk, but they will leave a Z symmetry at the boundary here. And now if we look what anyons do, so anyons, as before, were putting us excitations, right? We talked about excitations also with order parameters. We put a string of Z's, but we could also put some X here. And well, the role of X and Z swapped compared to the last slide. But you again see now you have a global Z symmetry. This is an order parameter, and this is this dual order parameter. And what they do is they indeed introduce a twist in the entanglement, right? They twist the entanglement symmetry. So depending on how the system behaves, this could make a twist. It could make an excitation. They're anyons, they should make excitations. So this is very much an analogy to what the order parameters before did, right? They twisted the system, but the order parameters before twisted the physical state. They created domain walls. But now we twist the entanglement in the system. We twist the system on the entanglement level. And this can be used to construct order parameters. Seeing how the system reacts to twists in the entanglement can be used to create order parameters for topological order by using these symmetries, by using these anyon strings, and the fact that we have this, excuse me, that we have this direct access to the entanglement level, which we usually don't have. And this is very useful to, for instance, mathematically classify the way different topological phases can arise with such symmetries, which is what we did in this work, but also to numerically study topological phases and phase transitions. And that's something I would like to illustrate in the next two slides. So one thing that we did is to study really a phase diagram with several parameters. So here you see 3 parameters on a couple of surfaces with some Z4 symmetry. And there's really a wide range of phases. There is a Z4 topological phase, a well-known toric code in different manifestations, in fact, a double semyon model, and then we can play with these parameters and see what happens. And we can measure order parameters. That's what you see in the left plot. And what happens as we go through a phase transition is that certain anyons disappear. They condense into the ground state. Other anyons disappear because they become confined. They cannot be separated anymore. And this all we can associate to order parameters. There's an order parameter measuring the condensation, a different one measuring the fact that a particle is deconfined. And as particles get confined, suddenly there's an associated length scale, which we can also measure and use to study the phase transition by asking how does it diverge. Or we can compute the correlation length as the anyon starts to condense. The correlation length diverges, which means the mass of the anyon, the inverse correlation length, will close, the gap will close. So we can really look at that. And in this case, we indeed got what we expected because we knew this phase transition could be mapped to an Ising model phase transition. But what we also did is we took a 2D quantum model, a model which is where we don't expect to see universal behavior of a 2D classical model. And what we did is we took the toric code model and we added a field in X and Z direction. And this model has a phase diagram with a topological phase here in the center and some trivial phase out here with different types of phase transitions depending in which direction we apply our field. And then we did variational simulations. We tried to find a tensor which minimizes the energy but keeping a Z2 symmetry. Now, this is not a Pauli matrix, but just a general representation of Z2. So a Pauli tensor is the identity, so we have more degrees of freedom. Oops, sorry. And am I out of time? I feel I still have 2 minutes.
You can take another minute. We started a minute late, but yes, you're
exactly.
getting close.
My clock says like 1.5 minutes left. Perfect. Okay. Right. So one thing we can do is we can, for instance, study this line where we ramp up the X field. And on this line, we actually know that the model can be mapped, the ground state of the model, to a 2+1, a 2D quantum Ising model. And one thing we can measure what happens, that charged particles will condense. And indeed, this matches exactly the curve we expect from the Ising model, the Ising magnetization. So you would think we fully understand this line, but it turns out if we measure what happens to fluxes, to the other type of anyons, they become confined. And it turns out the critical exponent for this confinement is something which is not known from the Ising model. Actually, we have no idea where this shows up. So if anyone knows this critical exponent, let me know. I would be very interested. And now you might ask, how can this be that given that this whole line here is known to map to the 2 + 1 dimensional Ising model, we see a critical exponent which does not show up in the Ising model. And the reason is that the mapping is only a mapping between the ground states of the two models, basically the closed loop space, if you know the toric code in the X spaces. But what we do if we measure this flux confinement, actually we cut open the entanglement and we twist the entanglement, and the state we get by cutting open the entanglement and twisting the entanglement is something which cannot be mapped to the Ising model anymore. So although we only have this ground state, which is basically a ground state which can be mapped to a 2 + 1 Ising model, we get order parameters, we see properties which are not there in the Ising model because we have access to this entanglement degree of freedom, which we can use to get out of that space. And we can also look at other lines like the marked lines here. And if we study, we will see that the exact curves will look different because indeed the exact curves are not meaningful, but the question is how do these curves go to 0? And we see that the critical exponents are always the same. So for all these different lines, we see the same critical exponents. We see the Ising critical exponent. And on the other hand, this non-Ising critical exponent, which really shows that we can also, and I should point out that the other lines, right, this line here and this line here cannot be mapped to the Ising model anymore. So this is something we could not probe at all, not even for this Ising part of the order parameter, if we would not have this tensor network and have access to these properties. So message PEPs allow us to study topological phase transitions by constructing anionic order parameters, which are defined right away at the level of the entanglement. And they give us access to properties which we cannot get hold of otherwise. And I guess with this, I should stop. So let me just leave the summary slide here. Maybe, should I briefly summarize?
Sure. If you want to, we can probably move your question and answer if you want to the breakout roundtable.
I'm also happy to stop here and take a few questions. Maybe
okay, sure. Okay, that's great. All right, thank you very much for the wonderful talk. And Angela?
Yeah, so thank you for the talk. So we have the first question here from Rishi Sridhar. He's saying, is an ABR law still valid for quantum circuits with all-to-all connectivity? And can you think of any instances where it could still work with such connectivity?
Well, I guess with all-to-all, we don't expect an area law, right? We indeed probably expect a volume law. On the other hand, it depends on the symmetry, right? If you think about a condensed matter system with an all-to-all connectivity, it has a very high degree of permutation symmetry, maybe full permutation symmetry. And then we know that states which are fully permutation invariant are actually not entangled, right? There's a Definetti theorem which tells us that these states, basically the bigger the system gets and the more permutation invariant it gets, the more classical, if you wish, it gets, or the less entangled it gets. So in that sense, if you have such a scenario, indeed, in some sense, you again have an area law, or at least you can find an alternative description where you don't need any entanglement and can capture all the relevant properties.
Great, thanks. So, I mean, I think we can move any further question to the roundtable discussion because it's going to be easier that way. So thank you very much for the talk.